All right, let's dive right in. Today we are exploring one of the coolest, most fundamental connections in all of physics, the invisible, powerful, and honestly, pretty surprising link between electricity and magnetism. So, to get started, here's a little riddle for you. What does a simple battery have in common with a compass? I mean, on the surface, they seem like they're from different planets, right? One gives you power, the other points you north. But as we're about to find out, they're connected by a deep, invisible force.
And you know the way this all started? It wasn't some grand, planned-out experiment. Nope, it was a complete and total accident.
So, picture this. It's 1820. A scientist named Hans Christian Ørsted is in the middle of giving a lecture. And right there, during a demonstration, he just happens to notice something. Something that would completely reshape our world.
The real beauty of what Ørsted saw was just how simple it was. He had a wire hooked up to a battery, and sitting nearby was a regular magnetic compass. The second he connected that circuit and a current started flowing through the wire, bam! The compass needle, which should only ever react to a magnet, suddenly twitched. The electric current was acting like a magnet.
And that was the big deal. That tiny little twitch was the very first proof that electricity and magnetism aren't two separate things. They're basically two sides of the same coin. A moving electric charge creates a magnetic effect. It's as simple as that.
Okay, so this just opens up a huge can of worms, right? What is this invisible influence? If an electric current is making a magnetic effect, how can we possibly see what this invisible force field even looks like?
Well, let's start with something we're all familiar with, a regular magnet. If you've ever done this in a science class, you know it happens. You sprinkle tiny iron filings around it, and they don't just land in a random pile. They snap into this incredible, beautiful, organized pattern, literally revealing the invisible shape of the magnet's influence. And that region, that pattern of influence, is what we call a magnetic field. Those lines that the iron filings trace out are called field lines, and you can think of them like a map for this invisible force. And these field lines, they're not just random scribbles. They follow some very strict rules. They always form closed loops, flowing out from the North Pole and circling back into the South Pole. Think of them like invisible highways. Where the lanes are really close together, the force is super strong. And just like lanes on a highway, these field lines can never, ever cross each other.
All right, so we've got a handle on what a magnetic field looks like. Now let's circle back to Ørsted's discovery and figure out what the magnetic field of a plain old electric current looks like.
But here's the puzzle, right? A wire is just a wire. It doesn't have a north and a south pole like a bar magnet does. So how on earth do you know which way its magnetic field is pointing?
It's wild, but the answer is literally in the palm of your hand. It's called the right-hand thumb rule. If you imagine grabbing the wire with your right hand and you point your thumb in the same direction the current is flowing, the way your fingers naturally curl around that wire shows you the exact direction of the magnetic field. It's so simple, but it's incredibly powerful.
Okay, so knowing the rules is one thing, but the real question is, how do we actually use this? How can we take that pretty weak magnetic field from a single wire and pump it up to make it stronger and more useful?
So, how do you beef up the field? It's actually a really clever, logical progression. A straight wire has a kind of weak field, but if you bend that same wire into a loop, the field lines start to get concentrated in the middle. Now, what if you stack a bunch of those loops together into a coil, what we call a solenoid? Well, then you get this super strong, really uniform magnetic field right down the middle.
And here's the really cool part. When you look at the magnetic field from one of these solenoids, it looks exactly like a good old-fashioned bar magnet. It's got a north pole on one end and a south pole on the other, just like you'd expect. But here's the game changer. With a solenoid, you can turn the magnetism on and off just by flipping a switch. And then, if you really want to crank things up, you stick a piece of soft iron inside that coil. That amplifies the effect like crazy, and you've created a powerful, controllable magnet. And that, my friends, is an electromagnet, the secret behind everything from giant scrapyard cranes to the tiniest electric motors.
So far, we've used electricity to create a magnet. Okay, now for the grand finale. What happens when you take our wire with its own little magnetic field and you stick it inside the field of another, bigger magnet?
This is where the magic happens. The two magnetic fields, the one from the wire and the one from the permanent magnet, they start to interact. They push and pull on each other. And the wire itself actually starts to move. We've just turned electricity into real physical motion.
And, you guessed it, there's a handy little trick for this too. It's called Fleming's left-hand rule. If you take your left hand, point your first finger in the direction of the magnetic field, and your middle finger in the direction of the current, your thumb will magically point in the exact direction of the force. This simple rule is literally the secret sauce behind every single electric motor out there. That idea, turning electricity into motion, is what makes our modern world go round. But for that to work, you need electricity in the first place. So let's take a quick peek at the system that brings all this power right into our homes.
You've probably heard this number before. In a lot of places around the world, the power that comes out of your wall sockets is 220 volts. You can think of that as the electrical pressure that's pushing the current along to power your stuff.
And to handle that power safely, you've got this 3-wire system. The live wire and the neutral wire are what make the circuit work, but the real hero here, the one that keeps you safe, is the earth wire. If something goes wrong and a live wire touches the metal case of an appliance, that earth wire gives the electricity a safe path to go straight into the ground, which prevents you from getting a nasty shock. It's a really simple but totally life-saving bit of engineering.
And this whole connection is not just in our gadgets and our walls, it's literally inside of us. The tiny electrical signals firing between the nerve cells in your body actually generate their own incredibly weak magnetic fields. And modern medicine has figured out how to detect those tiny fields, which is the basis for magnetic resonance imaging, or MRI, letting doctors see inside our bodies without making a single cut.
So we started with a simple observation. An electric current creates a magnetic field. We've seen how that simple idea basically built the modern world. Which leaves us with one last, huge question. Can we reverse the process? If electricity can make a magnet, can a moving magnet make electricity? Well, that's a story for another time.